And she said,
hi again. Hope you guys are doing well. I'm going to talk about today in Bed Talks, 10 Talks from my bedroom. I'm going to be talking about Chapter 12 and Chapter 13. So the goal for this next two videos are going to be kind of a review of what we've done in the past, before the virus, I guess, kind of just the point. So I'm going to tackle Chapter 12 in this one, and then Chapter 13 in the next video. So Chapter 12, what are the main important highlights that we need to remind ourselves of? Well, the goal, right, of this whole entire chapter, at least to start off with, is to come up really basically with the idea of vectors and what we can do with them, how we can write equations of lines and planes with vectors, and also at the end, understanding quadratic surfaces. So at the most basic level, let's start to talk about vectors, right? That's kind of our goal. So as a reminder, what a vector is, a vector has two things. It has length and magnitude, right? So if I give you a vector A, I can think about this maybe as component-wise, right? This vector A here is A1, A2, and A3, and it's going in the direction of A1 in the X direction, A2 in the Y direction, and A3 in the Z direction. We also note that the length of A, as we call it the magnitude or the length or the norm, a couple different names we have for it, is just equal to the distance. So A1 squared plus A2 squared plus A3 squared. A nice, simple, important thing from the Pythagorean theorem. Now, a couple of interesting things to note, right, is if I had, a vector like this, right, and I have a vector like this. Let's say I have A and B. One question you might ask is, can I combine vectors? How can I combine vectors? There's a couple different ways that I can do that, right? So, and we will try to tackle some of those ways right now. Now, in this case, oh no, where did my eraser go? Oh no, there it is. I'm back, I found it, sorry. Let's say I have a vector A and a vector B. Can I add them? Can I subtract them? Can I do these things? Yes, you can. How do I think about adding vectors, right? What we thought about adding vectors, geometrically, if I wanted to do A plus B, how do I do this? Well, the first thing I do is I draw out A again. Then what I do is I put B from tail to tip. So what I do is I put the tail of B at the tip of A. Something like this guy. And then what I do to find A plus B is I take A plus B, something like that. So A plus B. And that's A plus B. As you can probably see very nicely, if I started off with B instead, and then added A, I get to the same exact thing. And this is kind of the idea of the parallelogram law, that I can go A plus B is equal to B plus A, which is very nice for us. It doesn't matter which way we do it. If I was to add vectors together, for instance, if I had A is equal to 2, 3, and B was equal to 1, -1, if I did A plus B, again, I could just add the components. So I get 3 and 2. I just 2 plus 1 is 3, and 3 minus 1, minus 1 is 2. And that's kind of my goal, right? So I can just do this very nicely. Another thing you could do is if I had A and B again here, I could think about the idea of scalar multiplication. Now, what does that mean? What does multiplying vectors mean, right? Is if I have C times A. What basically it's saying is it's stretching or compressing or flipping the directions. So in this case, you kind of imagine there's like a 1 outside. And what we would like is, if I had A plus A, it would make sense that this would be 2A, right? Just 2 times the vector, right? I had A and I had A again, this entire thing's 2A. That's kind of what happens. So if I have A like this, you kind of imagine that 2A is just double the length in the same direction. If I did 1/2 A, probably a little bit smaller because I'm just taking a half of that vector A. Remember with vector notation, we always need to include this little arrow over to make sure we know what our vectors are. What happens if I do a negative? Right, a negative here is flipping the entire direction. So for instance, negative A is like that. And we can also do negative, 1/2 A. We can combine them. And similarly, if I had, if I had 2, times 2 and 5 or something like that, maybe 2 times the vector 2, 5, again, I could just move this through and do what I want, right? That's that. Now, lastly, can I subtract vectors, right? We're thinking about multiplication a little bit differently. We'll get that in a little bit. Just kind of a reminder there. So, well, what if I wanted to subtract A and B? What if I wanted to subtract them, right? So if I thought about A minus B, there's a couple different ways you could think about it. One is to say, okay, well, this minus sign, I can kind of flip this and think about this as A plus a negative B. So for instance, if I take A, well, B here, I know negative B, it's going to be something like that. So I can just add that, negative B, and then connect. Something like this, A minus B. That's A minus B, just like that. There's another way you can do it, and I think it's a little bit better to think about it this way, a little bit easier, and it's going to help us more geometrically going forward, the idea of this. So if I connect A and B, I'm going to start them from the same exact point. That was a very long A. That was A, and then B, something like that. Here, something like that here. A little bit longer. Now, what we're going to do to find A minus B, if I want to find A minus B, I'm going to connect the tips of A and B. Now note, I am starting them at the same exact point, right? I'm starting them at the same point here. And what I'm going to do is I'm going to go in the direction of A. So I'm going to start from B and go to A. Like that. And this is A minus B. And as we see here, these two vectors are basically the same vector. I've drawn it a little poorly, but these are the same exact vector if you find this out. So this is a little bit better geometry. So that basically means you're connecting the tips. And the vector that you end at, this tip that you end at, is your vector that you're being subtracted from. So A minus B, you start at B and you go to A. That's the idea of subtraction. Now, kind of extending this, you might start just thinking to yourself, well, okay, so why do I want to scale and multiply? Why do I want to do that? The easiest thing to remember, especially when going forward from this, is, how do I make a unit vector? What does a unit vector actually mean? Especially with scalar multiplication. So I have a vector A, I love to call it A1, A2, A3. It's fine, we can make this as general as possible. I want to make a unit vector. The idea of a unit vector, again, is I have a vector here that I want this to be 1, right? I want the magnitude to be 1. So if I want the magnitude of this vector to be 1, it's not guaranteed that it is, right? We have that the magnitude is a squared, b squared plus c squared. I want to think about it this way. I want to multiply a number times a, and I want this to be equal to 1, right? Now, if I want this number multiplied by a to be equal to 1, right, the magnitude of that, I can move out the c, right? I can move out the c here. Think about this, times the magnitude of a is equal to 1. And what I could do is I can multiply, I can move this down 1 over the magnitude of a. I know this is a positive number, so I can just get rid of this c. All nice of it. So therefore, what I'm going to do is if I want to multiply a number times a to get me a unit vector, what I'm basically doing, right, is if this is my vector a, I want to scale it down so it's still in the same direction, but only has a length of 1. And to do this, I take a and I divide it by the magnitude of a. So as an example, as a quick example, right? If I have the vector, 2, 3, I want to find the unit vector for this. I would find the magnitude, which is the square root of 4 plus 9, or the square root of 13. And so therefore, a over the magnitude of a is going to be 1 over square root of 13, 2, 3. And this vector is going in the same exact direction, but since this number is greater than 1 here, I'm going to be shrinking it because 1 over that's going to be less than 1. Okay. That's the idea of a unit vector. That's kind of the main goal. Now, continuing forward onto this, how do I multiply vectors? It's not easy to do that, right? And dividing vectors is really not well defined. So how do we think about multiplying vectors? It's 2 ways. And they give us 2 very, very, very important things. First thing is the dot product. This tells us a lot. Dot product tells us a ton of things. Well, the first thing is how do we compute the dot product? There's 2 ways. We usually say a dot b, this dot right here. What we can do instead, I'm going to assume that this is a 2-dimensional thing, but it can extend very quickly to 3 dimensions. A dot b here can be written I'm going to take A1 times B1, the components multiplied by each other, plus A2 times B2. Here. I'll extend it to 3. It's fine. I have enough room on that. So as again, what I'm doing is it's a number. This is a number. This is a scalar quantity. It gives me a number for this. It's a very important thing to remember. So if I take a dot product, I'm taking each component and I'm multiplying it and then I'm adding them together. You can find through some trig identities, some fun trig identities, that this is equal to the magnitude of A times the magnitude of B times cosine of the angle between A and B. This angle, this is A and this is B, this is theta. It's the angle between them. And this gives us a lot of insight, actually. It tells us what does the dot product actually mean? What does it physically mean? Because if you think about it, A dot B can be one of 3 things. It could be greater than 0, equal to 0, or less than 0. It could be one of these 3 things. Now, if it's greater than 0, we can take a look here. And this guy is actually the most interesting one. Sometimes, this is really important or this is really important. In this case, what I'm going to say is this is probably the more important one from a physical standpoint. This is really easy to calculate. From a physical standpoint, to tell us what everything means, this definition is going to be much more vital. If this is greater than 0, well, I know that magnitude of A and magnitude of B have to be greater than 0. So we take a look at cosine of theta. Cosine of theta here, that has to be, this means that cosine of theta has to be greater than 0. So what does that mean? If cosine of theta is greater than 0, as a reminder where cosine of theta lives, right, if it's greater than 0, that's where x is positive. So over here, which means that I've got to be between maybe like a 0 and a 90-degree angle. So that means that my angle here is acute. That means A and B make an acute angle. If it's less than 0, I'm going to skip this one in the middle 1 second. If this is less than 0, this means that cosine of theta is less than 0, which means I'm over here, which means that they make an angle from a 90 to 180 degrees about, which means then they're obtuse. They make such a long angle like that, at that angle. And lastly, and probably the most important aspect of this, if A dot B is 0, that means that cosine of theta is 0. If cosine of theta is 0, what does that tell me? Well, cosine of theta has to be 0 at a 90-degree angle. So they're orthogonal. And that's probably the most important one to remember going forward. If A dot B is 0, we have an orthogonal angle. So that's kind of all the things we really need to know. There's some really nice properties that you can talk about projections. Projections aren't going to come into extreme play going forward here, so I'm not going to review them too much. If you have any questions about them, feel free to ask me. But for right now, we're going to kind of scale back on the projections a little bit because that doesn't come too important. These are much more important concepts. Now, the next thing that we want us to kind of discuss is, well, what if I want to multiply them and get a vector? That comes from the idea of the cross product. So what could be very helpful? Let's say I give you A and B, A1, B, A2, A2, and A3. And I give you B and B1, B2, and B3. And my goal is to find a vector. My goal is to find a vector, in this case, that is orthogonal to both of them. So for instance, if I found A dot B is equal to 0, some vector C, such A dot C is 0, and B dot C is 0. I want to find a vector C that does this. Now, I hope you'd agree that this is almost impossible to do in 2 dimensions. You have to have very, very specific vectors for that to happen. They have to be actually, exactly opposites of each other for this to happen. This only can happen in 3 dimensions on the regular. Now, with this in mind, if I have this now, well, I need to find my vector C. Through some calculations, you can actually find that the cross product gives you this vector C. The cross product then gives you specifically all of the vectors, well, specifically a single vector that is orthogonal to both A and B. You got to think about this as the axes, right? If I have the x-axis and the y-axis, I could take the cross product of those 2 vectors and actually get the z-axis, or any single corner in a room. So if I do this here, A cross B, that's what we usually know this. This is going to be a vector. Remember, this is going to be a vector. We had in the past, right? In dot product was a scalar. This is going to be a vector. It gives me a vector that's orthogonal. And what we do is we calculate the cross product using a determinant. So I, j, and k are my standard basis. I, j, and k, right, in the x direction, the y direction, and the z direction. And I have a1, a2, and a3, b1, b2, and b3. And I calculate this as thus. This vector, a cross b, gives me, and this is really important, this gives me a vector orthogonal to both a and b going forward. Now, what other things can we talk about here? Right, what are the interesting things we can do this? So an important concept going forward is going to be the following. Well, what happens if I take a cross b now, still with the cross product, still the ideas of the cross product here. What happens now if I take two vectors, a cross b? How do I know the right-hand rule, right? How do I know what direction it goes in? So if I have a here and I have b here, what if I want to calculate a cross b, which direction is this pointing in, right? And the idea here is using the right-hand rule. What we do is we put our right hand, our fingers going out in the direction of a, like that. What we do is we curl them in the direction of b. And if you note here, my thumb is pointing directly into the board. This means that if it's pointing directly into the board, that is where a cross b is. A cross b lies going directly into the board. If I had b cross a, I would put my fingers here, I would curl up in this direction, and b cross a is pointing outward. So you might think to yourself, well, okay, that's actually kind of interesting. So a cross b is in the exact opposite direction as negative b cross a. That's true. So because of the right-hand rule, a cross b, if I flip it, flips that side. That's pretty nice. So we'll give you two different directions. Another important fact to ask about is, well, what happens if this occurs, the zero vector? All right, why does that occur? Now, in order to do this, what I'm going to do instead is I'm going to take a look at what the magnitude of a cross b is, because you can find what the magnitude of a cross b is. It's the magnitude of a times the magnitude of b times sine of theta. Now note the distinction between our dot product and this. This is a sine instead of this is cosine, right? Cosine was dot product and sine is cross product. Now, if a and b are non-zero, which, you know, 7 million times out of 7,000,001, they will be. It won't be zero. Sine then, if I want the magnitude of the vector, the magnitude of this vector to be zero, right? I want this to be zero. I would need sine to theta to be zero, where theta again is the angle between them. When is sine of theta being zero? Well, it's actually zero when theta is zero. So what does that mean? That means that they have to be on the same line. To be something like this. A and B. If they're on the same exact line, you kind of see that, you know, the right-hand rule is going to fail. Like, where do you curl your fingers, right? And they won't really know. So therefore, a cross b is zero when a and b are parallel. Parallel. I cannot spell today. Boop, boop, boop. They're parallel. There you go. So A and B are parallel. So if A and B are parallel, then A cross B has to be zero. We have to come up with a different way to come up with a normal vector of some sort. Now, this gives us some really nice things. Now, I want to just talk about this really, really quickly. What does this actually tell us and what we use this for? This is a very quick aside. If I take a look, I'm going to keep that formula up there really quickly. If I take a look at A here, I take a B, I consider the vector, I consider the, the parallelogram formed by A and B. Something like that. Here. I want to find the area of this guy. Let's say if I want to find the area of the vector of the parallelogram formed by A and B. Well, you can kind of think about the area is going to be, base times height, as I have in the past, base times height. So what's the base here? I hope you'd agree that this vector right here, this magnitude is going to be the magnitude of B. Right, so the base here is literally just the magnitude of B. Okay. Now, going forward, well, what's the height? Well, the height actually is dependent on this this height right here. And how do I find that? Well, I have my theta. My theta is my angle between A and B. I know the hypotenuse, the length, is the magnitude of A. I know it's going to be opposite, right? A theta is going to be opposite. So SOHCAHTOA, I know that I have opposite over opposite over hypotenuse, right? So I'm going to have my opposite, so sine is going to be my aspect here. So I'm going to have to multiply this by the magnitude of A times sine of theta, right? That's actually what this is. And so if you notice here, they're the exact same. This is exactly the same. So because of that, what the magnitude of this tells you, it's actually the area of parallelogram formed by A and B. And again, it would make sense that the area of the parallelogram formed by the same vector or vectors that are parallel should be 0. Yeah, that's kind of it. So that's up to section 12.4. Now, the last thing we're going to do before we finish up, and I'll go on to another video for section chapter 13, is the idea of lines and planes. Right, the main goals of lines and planes. Because we're going to need to write a lot of lines and planes. Now, just kind of looking forward, chapter 14 and 15 don't require a ton of, writing equations of lines and planes. They don't require a lot. Chapter 16 will. When we get back to vectors, we get back to vector calc, it's going to be imperative. I mean, even actually I lied. In chapter 14 and 15, we're still going to be working with planes, especially thinking about like cross-section system. So how do I write the equations of the lines? Let's talk about that first. As a reminder, if I want to think about the line like y equals mx plus b, right, this is b. Right, if I just had 2 dimensions here, it's very, very easy to think about slope, right? The idea of slope here, m, is I go 1 over and m up. That's the idea of slope. Now, in 3 dimensions, it's kind of tough to think about slope, right? Because I have to go x, y, and z, right? I have to think about ratios maybe between x's and y's and z's, and that's kind of just really difficult just in general. So slope doesn't really come into play that well. Right? At least a single number doesn't come into play very well. So I have to come up with a different idea. So let's come up with the idea actually still in 2 dimensions, because I'm not very good at drawing in 3 dimensions, and I will not be doing that for you. But let's think about this in 3 dimensions. At least think about everything in 3 dimensions and all that in 2 dimensions here. Let's draw a line. Something like a line like this. And I want to find the equation of this line. What I'm going to do instead is I'm going to use vectors. So how am I going to do this? I just talked about the geometry of addition of vectors, so we might as well use that. So I'm going to take any point. Let's pick any point. I'm going to pick a point here. This point right here on my line, I'm going to name this R0. This is a vector going to that point. Okay. Now, let's say I want to find another point on the line. Let's say I want to find this point on the line. Well, what I could do is I know which direction I have to go in. It's actually this direction. Maybe it's some v, right? Some direction v here, which goes in the direction of this point. And what I can then do is I know that this vector right here gives me another point on my line. If you notice here, what's actually happening is I'm doing R0 plus v. Right? I'm just adding that. Now, this is just the same geometry of vector addition. In a similar way, I can keep extending this, going forward and say, okay, what if I multiply it by 2v, right? Maybe in the same exact direction, I can get another point, right? Maybe this is 2v. I get another point up here. So this is R0 plus 2v. Maybe I can go backwards a little bit. Maybe this is negative 1.5v because I have to go backwards now. And this right here is R0, minus 1.5v. If you see here, what's basically happening is I'm taking R0 and I'm multiplying it by a number times v, right? This direction of v. In a more general sense, I say R of t is equal to R0 plus t times v. And this is the equation of a line, where t is my parameter, R0 is my starting point, and v here is it's called the direction vector. It's going to become very important, actually, going forward. And either understanding the idea of direction vectors and understanding the ideas of how to write the equations of lines and tangent lines and stuff like that is a really important concept, because tangents are a way that we can approximate values. So this is the equation for a line. Now, I can restrict some things, and I can make some important changes to this formula if I wanted to. For instance, if I want to come up with a line segment instead, what I could do instead here, the idea of a line segment, it's basically I'm restricting it. Let's say I want to go from, I have A here, and I have B here. And I want to just come up with the equation just for this part of the segment. Well, if this is R0, and I'll call this R1, and again, I'm going in the direction, let's say I want to go in the direction of AB here. If I think about my geometry, this is R0 and this is R1, 2 points on my line. Well, what's this line? Well, if I think about the geometry that I just talked about, I'm connecting the tips of two vectors starting from the same position, which is subtraction, which is R1 minus R0. So what I could do instead is I could actually replace this V with R1 minus R0 equals, R0 plus T times R1 minus R0. That's my direction V. And now what's really interesting, if you notice here, at time equal to 0, would you agree I'm at R0? This entire thing goes away. At time equal to 1, I'm left with R0 plus R1 minus R0. The R0s cancel, and I'm left with R1, so I'm at point B. And so therefore, if I restrict this time between 0 and 1, that's my line segment. And this is another way you can write the idea of a line segment. Those are the main ideas for a line. There's many different ways you can find the equations of a line, as we have talked about before. Maybe the intersection of two planes, maybe knowing if I'm going from point A to a point B, maybe some other ways too. There's a lot of different ways that we've tackled. This is at least the general idea. And lastly, let's talk about the idea of planes. How do I write the equations of those? Well, you kind of think about the idea of equations of planes, if I even take out my map here. Right. If you notice, this is kind of the idea of a plane, the idea of an infinite plane. But what we want to do instead is think about that. Well, on this plane completely, this vector is similar at every single point. Right? We know this vector that's actually perpendicular to the plane itself is the same everywhere. So maybe this is a way we can kind of come up with that. And it actually is. It's actually the way we think about these ideas of planes. So if I want to just draw this out relatively, if I can, if you bear with me for a second, take a point on my plane. Let's call this point R0. Okay? If I pick any other point on this plane, any other point here, let's say I pick, oh, I don't know, let's pick this point. I'll name this point R. If I connect these right here, if you'd agree, if I connect any 2 points, on any plane, that vector has to be on that plane. I connect any 2 points, right? So because of that, this vector here, which I think is pretty nice to see geometry-wise, as we kind of just talked about, it's going from tip to tip, is R minus R0. And now, that's R minus R0. So now going forward here, what can I tell you about all these vectors? Every single vector is R minus R0. I can go through R. R is very general. But I know that there's this vector here, which I just discussed, which I'll call N. It's called the normal vector. It is perpendicular to the plane. And now if you notice here, R minus R0 and N, because R minus R0 is on the plane, and N is perpendicular to it, they have to be orthogonal. And because they're orthogonal, what can that tell me? How can I write that down? Well, I know the idea of the dot product. The dot product between them has to be 0. So the normal vector, R minus R0, has to be 0. This is called the vector equation for a plane. Okay, and now going forward here, right, I can write here more specifically, if I let N be A, B, C, I let R be more general as an X, Y, Z. I can't really write a little farther here, I don't have enough space. R0 is more general, x0, y0, z0. If I kind of just, you know, crank the wheel, I can get this formula. I'm going to break it down here. That we utilize every single time we write the idea of an equation of a plane. Where n is ABC, and x0, y0, z0 is a point on my plane, any point on my plane. So I have two things always. I want you to go back to this idea. I have two things that I always need for a plane: a normal vector and a point. I need two things always for a line: a direction vector and a point. If you have these two things, many times there's many different ways we can get to it. You know, thinking about maybe the intersection of two planes, maybe thinking about these things here. But overall, these are the general ideas too. I know I didn't discuss in the lines, but there's the idea of parametric equations and the idea of symmetric equations. Those are important aspects too. And I'm just kind of doing just a general review here. So that's it. If you have any other questions about these kinds of concepts, let me know, and we can just kind of discuss them in the future. But it's important to, at least for you, to kind of remember that this chapter 12 stuff does not go away. It will not go away. All this stuff, we'll talk about dot products, we'll talk about cross products, we'll talk about planes and lines going forward. And it's really important for you to know that, because if you understand the geometry, it becomes so much more helpful and important once we start getting the much more higher concepts, especially chapter 16, which becomes very, 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 you know, it becomes very, very complicated. It does. There's a lot of different things. We're combining everything. And it comes to this beautiful part at the end. But that's the idea. Okay. If you have any questions, let me know. And I'll come back in a little bit to talk to you about chapter 13. But let me know if you have any questions, and have yourself a great day.